Okay. Okay, so this can be written as A11M11, where M11 is this, right? And minus A12 times M12, which is this, plus A13 times M13, which is this. Okay? Now the rule for Mij, and we could do an Mij for any element of the matrix, right? Of any matrix of any size. It's just the matrix you get when you eliminate row I and row j, right? And this is called the Ij minor. Okay? So we've got this, and this represents this. This summation represents this sum. Okay? Because it's A11M11, there it is, minus A12M12, plus A13M13. K goes from 1 to 3. Then AIK, MIK is A11M11, which is this, right? A12M12, A13M13. The only thing we don't have in there is this minus sign. How are we going to handle that? Well, I'm just going to say, okay, and now we just left myself room, but I could have left myself more, but I take negative 1, okay, and raise that to the power 1 plus k. So now if k equals 1, 1 plus k is 2, negative 1 squared is 1. So this is what we get, right? If k is 2, 1 plus k is 3, negative 1 raised to the third power is negative 1. That's where we get our negative, right? Yeah. And so forth, okay? Now, the neat thing about this is, if I replace 3 by n, I have the formula for any matrix. Okay? That makes sense? It gets even better than that, but let's stick with this for a minute. So if I have a 4 by 4, well, it's just, it'd be this one times what you get, the 3 by 3 that you get, right? Of course, that 3 by 3 would have to be reduced down to 2 by 2, so it gets out of hand real quick. Yeah. By the time you get to a 10 by 10 matrix, you have over 3 million 2 by 2s. Okay? Actually, it's like 360,000 2 by 2s, but then you have like, So that's a little better than 3 million. If you go 11 by 11, you got over 3 million. Okay? So it gets out of hand real quick. So you don't use this to find determinants. You know what you do to find determinants? Well, a lot easier with a 10 by 10 than doing 3 million calculations is you row reduce it, which takes less than 100 row operations. Okay? That's a lot better. You can actually do that in a couple of hours and maybe less if you're quick. Okay? As opposed to the rest of your life. And when you row reduce, you keep track of any time you multiply a row by a number. Okay? Or reverse rows. You keep track of the numbers you multiply by and the number of times you reverse rows. If you reverse rows an even number of times, you don't change the sign. Otherwise, you change the sign of what you get when you multiply all the numbers you multiply by rows. In other words, you keep track of your elementary matrices and their determinants. But we'll see that. Okay? So you could calculate a 10 by 10. Your chances of getting every step right are pretty minimal, doing all the arithmetic correct. So I'm not going to ask you to do anything bigger than 9 by 9. I'm not. I'm not going to ask you to do anything bigger than a 4 by 4, unless there are some shortcuts, and there often are. Okay, well, that's kind of a preview. Okay, now, or I can say, if I let Cij equal negative 1 to the I plus j times Mij, then I don't have to write the negative 1 to the I plus k here. I can just write C1k. Okay? Does that make sense? Okay? It also turns out that we do the same thing with the second row. So we can do this with A21, A22, A23 with M22, N21, M22, and M23. Okay? Now, of course, since 2 and 1 is 3 and negative 1 to the third is negative, I'd have a negative this times what I get when I throw out this row and column, right? And then a plus this one and a minus this one. It just works out real easily. Okay? So it doesn't have to be the first row. As far as that goes, it doesn't have to be a row. It could be any column. But it can't be the diagonal or anything else. It's either a row or a column. Okay? So the same works for any row, and we can write the summary of that in this notation. Okay? And the summary is simply that the determinant of A is a sum from I equals 1 to n, okay, of I'll make it k equals 1 to n, okay, to imitate this because k is the thing that's changing. Okay, k equals 1 to n of this for any fixed j. Now, if j is 1, then this is just, and I forgot my A, J, K, right? If j is 1, this is just A1K and M1K, right? And this is j is k, right? Yeah, k is k, but j is 1. Well, that just reduces to this, 1 plus k, right? If j is 1, then this is k plus 1, which is, of course, the same as 1 plus k. And A1k, well, if j is 1, that's what we got, right? And it'd be M1k. But we could do it for j equals 2. Okay? So I say for any fixed j, if I had written j, it would make more sense. Any fixed j between 1 and n. Okay? So for example, if you have a determinant where one of the rows is all 0 except for one number, then you use that row because all your cofactors except 1 are going to be 0, right? So you immediately reduce that just to a smaller matrix with a lot less calculation. Okay, so you look for rows of zeros. Not only that, you can look for columns because it works just the same for columns. The determinant of a matrix can be proven easily to be equal to the determinant of its transpose, where the rows become columns and the columns become rows. So we can say that this is equal to the sum for k equals 1 to n of negative 1 to the k plus I, a k, you know, I should have used I here. Okay, well, I'm gonna fix it, but right now it reads AKI, right? I's usually your first. There's no reason I can't use it here, but it's confusing, right? So I'm gonna fix it in a minute, but you still see the pattern. Okay? Well, that takes you down the first column, or the ith column, right? Except you want to call it the jth column, so I'm going to turn the camera off and make these j's into i's and these i's into j's, okay? So it'll look right. But you get the idea.